Hello all, I'm recording this on a Good Friday, therefore I will try to fly over the material because I want to do some other stuff, which includes socializing. It's not my most favorite thing in the world, but it's necessary these days. Okay, and I was very happy to see that a lot of people either commented or even messaged me about papers related to the UK curriculum. So this is one more paper from the UK curriculum, okay? So the title is Pearson Edexcel Level 3 GCE, and this is paper 1, Advanced Physics 1, which I believe is taken by year 13 students or whatever the final year of high school is in England, okay? And this one is kind of recent, excuse me. It's from May 2024. So let's dive in and see what's going on. Okay. In these tests, you have an hour and 45 minutes. So the general rule I always say in all my videos is to spend about a minute per mark. So if the question awards 10 marks, it should take you about 10 minutes and so on. Okay. Let's start with the multiple choice part of the paper. So first question, which of the following is the base unit for charge? This, of course, the coulomb. Okay, so this was an easy one. Option B is the correct one. Let's move on. Which of the following could not be accelerated by a LINAC? Okay, the electron can be accelerated, the proton as well, the uranium ion as well, but the helium atom cannot be accelerated because recall that an atom is actually electrically neutral, right? Because it includes both protons and neutrons. So you cannot accelerate anything that is electrically neutral. So you need some sort of charge. And the uranium ion actually has charge because you form that by removing, you strip the uranium from its electrons, so it becomes an ion, which means that it's positively charged, which means you can accelerate it, excuse me. So option B is the correct one. Question 3, a toy car moves up a slope at a constant speed as shown. The car is moved by a motor with a power output of 5.2 watts. The car gains gravitational potential energy of 0.4 joules in a time of 1.1 seconds. Which of the following expressions gives the work done in joules against resistive forces? Okay, so if we multiply 5.2 watts by 1.1 seconds, we will find the energy spent in this procedure, right? I mean, the energy given by the motor, okay? So let's write it as energy by motor, excuse me for my bad handwriting. But then we have to subtract from that the 0.4 joules of gravitational potential energy, and this will give you the energy spent on resistive forces, meaning that that's the energy needed to overcome these resistive forces and make the car move up the ramp. Okay, so the answer will be 5.2 times 1.1 minus 0.4, which is option B. Okay, so let me mention one thing that comes up over and over again in these types of multiple choice questions. For example, in these options over here, option C is totally wrong because you have watts divided by seconds. Okay, so that will give you joules over seconds squared. So option C is erroneously wrong in this case. Okay, and then option D is also very wrong, let's say, because you are adding the gravitational potential energy to the energy given by the motor, so that doesn't make any sense. So the only thing that might confuse you here is option A, but in option A you're multiplying. Again, you have a problem with units, okay, because 5.2 is has units of watts, and then if you multiply 0.4 by 1.1, you get units of joules times seconds. Okay, so you have inconsistent units in options A and C. And then option D has consistent units, but it's wrong. Okay, so you can even arrive at the answer by an elimination process. Okay, so this is my point. Excuse me for taking so long to explain. Okay, let's move on to questions 4 and 5, which refer to two small positively charged spheres, S1 and S2, suspended by threads as shown. Okay, which of the following vector diagrams shows the forces acting on S2? Okay, if we do the free body diagram first, we will see that if we go to sphere S2, we will have the tension of the string, right? That's the first force. We will have the repulsive force from sphere S1 to the right, and then we will have the weight that points down. Okay, so if you form a free body a vector diagram for these forces, this vector diagram should be a closed one, which means because the forces should add to 0, right? Because S2 is not moving. Let's go and inspect. Okay, A is actually the answer, okay? So the correct answer is A. This is because you have the weight over here, okay? And if you add the, let's call it F for the force, for the Coulomb force, okay? So if you add these two forces, you get the tension, okay? So this closes the triangle, and this means that the object S2 is in equilibrium. With B, though, you are adding the weight this way, and then you have the electrostatic force pointing to the left, so that's totally wrong. Then in option C, this force is correct because it's the weight. The force to the right is also correct because it's the electrostatic force. But then these two do not form a closed triangle. I mean, all the arrows have to point in the same direction pretty much, and they don't. So that's totally wrong. And then for the same reason, D is also wrong. Okay? I hope my explanation is clear. But remember that in a vector diagram, you have to form a closed triangle, which denotes, in the case of forces, a closed triangle means that forces are in equilibrium. If you're dealing with momentum, it means a closed triangle means that momentum is conserved, and so on. Okay. Question 5, not option 5. The electrostatic force between the two charges is initially F. The charge on S1 is doubled, whilst the charge on S2 is unchanged. The distance between S1 and S2 doubles. Which of the following is the new force on S2? Okay, I'm going to use a clean page to explain this. So let's examine the initial situation. So you have a charge Q, another charge Q. The separation between them is D, and they are in equilibrium. Okay, so you have the force to the left and to the right on the two spheres, and this force is equal to 1 over 4 pi epsilon naught times Q over D squared. Okay, now in the second scenario, we have a charge of 2Q to the left and the same charge Q to the right, and the distance increases to 2D. Okay, so again, the two forces will be equal. Don't get confused with that. Okay, this is because they obey Newton's third law. Okay, so the new force, which I called F prime, is 1 over 4 pi epsilon naught times 2Q times Q over 4D squared, right? So this is equal to pretty much, if we simplify that, we have 1/2 times F, the initial force from up here, okay? So the correct option is, let's go back, B, okay? Hope this makes sense. And let's move on. Okay, question 6. A square coil has sides of length L and carries a current I as shown. The plane of the coil is parallel to a magnetic field of flux density B. Which row of the table gives the magnetic force on the named side of the coil. Okay, and we have a table with two columns. The first column is the named side, and the second column is the magnetic force. Let's inspect what's going on and see if we can immediately eliminate some options. Okay, first of all, you see that in all four options, they give us a magnetic force. That doesn't make any sense for side QR, right? And side PS. And why is that? Let me know in the comments. Okay, pause the video, think about it, and write a comment. Why is the force 0 for QR and PS? Okay, now I suppose you came back after pausing the video, and the answer is that the current is parallel to the magnetic field lines, so it doesn't cut through them. So the force is 0. So options, let me see, options B and D are wrong. Okay, and we're left with options A and C. Okay, now option A says that on the side QP, so let's use red, on the side QP, the force is BI times the length to the left. Does that make sense? So we can use Fleming's left-hand rule, okay, with B pointing this way. So our index finger should point in the direction of B, and then our our middle finger should point in the direction of I, and in this case, I points that way, right? So I points that way. Therefore, the force, your thumb will, if you use your left hand side, your thumb will point into the page. Okay, so that's wrong as well. Therefore, C should be the correct answer. Is it though? So for RS, the current goes this way actually. Okay, let's delete that. So the current goes this way. So if we put our index finger in the direction of B and our middle finger in the direction of I, our thumb will point upwards, so out of the page. So C is indeed correct. Okay, so you see how in the multiple choice section of these tests, you can often just eliminate all options that are erroneously wrong and arrive at the correct answer even without knowing physics. Okay, so okay, you should know some physics. Okay, let's move on. Question 7. A length of wire has a non-uniform cross-sectional area. There is an electric current in the wire. Which of the following is not constant along the length of this wire? Okay, so the equation that comes to mind is I is given by the number of charge carriers times their charge times their drift velocity times the cross-sectional area. Okay, so the electric current is constant. The electron charge is constant, it doesn't change. I'm trying to think of scenario in which the electric charge can change. I'm pretty sure you can find, I mean, we're talking about advanced physics, like university or research level physics. Maybe there are scenarios in solid state physics in which charge carriers change charge as they move. Maybe, I don't know. I have to check. Okay, electron drift velocity does change, so it can change. So C is the correct answer. And D, the number of free electrons per unit volume, that's a characteristic of the material, so it doesn't change. So C is the correct option. Okay, question 8. A roundabout completes 5 revolutions in 20 seconds. Which of the following is the angular velocity of the roundabout? Okay, first of all, whenever you see an expression like this, you have to immediately think, oh, frequency, right? So, and why is that? Because you have 5 revolutions per 20 seconds, right? So this is 1 over 4 seconds to the minus 1. So that's 1 over 4 is 0.25, right? So 0.25 hertz. Okay, so when you read in a sentence 5 revolutions in 30 seconds, 20 seconds, 5 minutes, whatever, that's a frequency. Okay, but we are asked about the angular velocity, so we have to use omega is 2 pi times the frequency, and this yields 1 over 55 radians per second, which is close to 1.6, which is option A. So rads per second. Okay, moving on. Question 9. A person of mass 70 kilograms is standing on the floor of a lift as shown. The lift is accelerating downwards at 1.5 meters per second squared. Which of the following gives the normal reaction R in newtons acting on the person? Okay, so the equation of motion in this case is first, let's go to the free body diagram. How many forces are exerted on the person? 2. The reaction force, R, and the weight. Okay, but it's moving downwards with an acceleration A. Therefore, the equation of motion is m times g, which is the weight, minus the reaction, should be equal to ma. Okay, why is the weight taken as positive here? Because the acceleration is downwards in the same direction as the weight. Okay, so all we have to do is to solve for r. So r is m times g minus a, and if we plug in values, that's 70 kilograms times 9.81 minus 1.5. So that's option, what is it? D. Okay, moving on to question 10. An object was thrown so that it followed the path shown. Assume drag forces were negligible. The object was thrown with an initial vertical component of velocity u. The time taken to reach maximum height is t. Which of the following could not be used to determine the maximum vertical height s reached by the object? Okay, so let's examine the options. So option A is the standard Suvat equation. So this is actually used to calculate the vertical height. And in fact, let's go calculate it real quick. So the first step, excuse me, is to use the Suvat equation. So S is ut minus 1/2 gt squared. So if S is 0, so this is the case for the complete motion, and I'm going to show you what I mean. Okay, so if I start here and I move all the way up, let's say I need t half, okay, seconds, then I will need another t half to go back to where I started, which in the vertical direction is 0, okay? I hope this makes sense. So this is t. So if we said s equal to 0, s is ut minus 1/2 gt squared, so t cancels, and we can calculate t for the whole motion as 2u over g. So the t to reach the maximum height is u over g, and if we plug back to the Suvat equation, we will find u times u over g minus 1/2 g u squared over g squared. So the distance in the vertical direction is u squared over 2g. Okay, so you see how we actually used this Suvat equation, so that's correct. Then option D is actually the maximum height, which we just calculated, so that's a valid equation. And we are left with B and C. But notice that for C, let me go to the back of the paper because I'm pretty sure there is another Suvat equation we can use. So let me check this one. Okay, so that's one of the Suvat equations actually. And if we plug in the fact that the final velocity is 0, we uncover, so if, let me see, so if we plug, if v is 0, then s is 1/2 ut, right? And v, the final vertical velocity, is 0 once it hits the ground, right? So that's a valid equation we can use actually. Okay, I hope this is not too confusing. So let's go back. Therefore, C is also a valid equation. So again, S is U plus V over 2 times T, which is equal to U times T over 2 when V, the final velocity, is 0, and it is 0 when it hits the ground, okay? So the only wrong option is B, okay? So this was a little bit hard. So let's move on. Question 11, a film involves a gang of bank robbers making a getaway on a bus loaded with gold bars. Okay, that's, that's interesting. The bus spins out of control and ends up balancing on the edge of a cliff as shown. Pretty cool. Okay. State what is meant by the moment of a force about a point. So let's write this as an equation. So the moment is equal to the perpendicular component of a force, right, times the distance to the pivot point. Okay, so that's the moment of a force. Okay, B, the bus is balanced on a pivot that is a distance y from the center of the bus. The center of mass of the gold is 1.5 meters from one end of the bus. The center of mass of the bank robbers is 1 meter from the other end of the bus, as shown. Okay. So the unloaded bus can be treated as a uniform body with a weight of 32,000 newtons. Calculate the distance y when the bus is balanced. And they give us the length of the bus, the weight of the gold bars, and the weight of the bank robbers. So pretty much we will take moments about the pivot. Okay, so let me demonstrate it here actually. So the weight of the bus, that's a subscript, times y, right, plus the weight of the robbers times 4.5 plus y. And I got the 4.5 from the fact that the bus is 11 meters long. Okay, so that's 11 meters. Therefore, the middle of the bus is at 4.5 meters, right? So from the pivot, the distance of the robbers from the pivot is y plus, wait, something's wrong here. Oh, yeah, what is wrong is that the middle of the bus is at 5.5 meters, excuse me. Okay, so the robbers are 1 meter from the edge of the bus. Therefore, they are 4.5 meters away from the center of mass of the bus, plus y from the pivot. So we have 4.5 plus y. Okay, and this should be balanced by the weight of the gold times 4 minus y, which is the distance of the center of mass of the gold from the pivot. And you can see this from the fact that the gold bars are 4 meters from the center of mass of the bus, from the center of the bus. And then we have to subtract y. So this distance is pretty much 4 meters, right? And we have to subtract 4 meters from y to find the distance from the pivot. Okay? So I hope this is not too confusing. Let's turn the page and write down the numbers. So 32,000 times y plus 39,150 plus 8,700 y is equal, I hope I didn't copy down anything wrong, it's equal to 124,000 minus 31,000 y. Therefore, we have 71,700 y is equal to 84,850. Therefore, y is 1.18 meters, so about 1.2 meters. Okay? Question 12. Electrical power is transmitted from Norway to Britain using a cable led under the North Sea. I actually didn't know that. The following information is published on a website. The cable has a diameter of 15 centimeters and a length of 720 kilometers. It is made of copper of resistivity 1.5 times 10 to the negative 8 ohms times meters. The electrical power transmitted from Norway is 1400 megawatts, and the transmission potential difference is 1100 kilovolts. The efficiency of this process is almost 100%. Deduce by calculation whether the claim for efficiency is correct. Okay, we have a lot of information. So first of all, let's find the resistance of the cable. So the resistance is given by the resistivity of copper, right, times the length of the cable over its cross-sectional area. Okay, so we have, and this is then equal to rho times the length over pi d squared over 4. Okay, so this is equal to 4 times 1.7 times 10 to the negative 8 times the length, which is 720,000 meters, over pi times the diameter squared in meters, right? So this is simply 0.693 ohms. Kind of low for a very long cable like that. Okay, so now the second piece of information is that we have 1400 megawatts transmitted at 1100 kilovolt potential. So the power is I times V, right? So we can calculate the current that flows through this cable, right? So I is P over V. So that's 1400 times 10 to the 6 over 1100 times 10 to the third. So the current is 1273 amps. Okay. Now the power lost because of the current flowing through this cable that has resistance of about 0.7 ohms is P is I squared times R. And we just calculated the current that flows through this cable. So we can use that to have 1273 squared times 0.693 yields 1.12 times 10 to the 6 watts. So the efficiency is equal to 1400 megawatts minus 1.12, because 1.12 times 10 to the 6 watts is 1.12 megawatts, right? Over 1400 times 100, right? So from those 1400, we lose 1.12 due to the cable having some resistance. Therefore, if we perform the calculation, we find 99.9%. Okay, so that's remarkably efficient. Okay, so the information in the website is correct. Okay, so I put a tick there, meaning that the claim is correct. I hope this makes sense. If it doesn't, ask me in the comments and I will explain further. Okay, moving on to question 13 now. Okay, question 13. Beams of antiprotons are often used in particle physics experiments. Show that the rest mass of an antiproton is about 900 MeVs per c squared. I haven't done this in a while, but sometimes I mention things from physics that interest me. So at CERN, there is the antimatter factory, I believe it's called, that studies and creates antiprotons, anti-hydrogen, anti-helium, stuff like that. So they make the same elements as the known ones, but in their antiparticle form. So, for example, an anti-hydrogen will have an antiproton in its nucleus and a positron orbiting around that nucleus. I find these things fascinating. If you guys are watching from CERN, hire me. maybe temporarily. I just want to be there and see how things like this work. I mean, it's really interesting. For those of you who are students, look into it. The antimatter factory, something like that, at CERN. All right. So, question A: show that the rest mass of an antiproton is about 900 MeV per c squared. So, okay, let's use our friends Einstein's c squared, arguably the most famous equation in physics. Okay, the mass of a proton is 1.67 times 10 to the negative 27 kilograms times the speed of light squared. Okay, this yields 1.5 times 10 to the negative 10 joules. And if we divide by 1.6 times 10 to the negative 19 joules per electron volt, we will find 939.38 MeVs is the rest energy of the proton. Okay, now how do we find the rest mass? So we apply the same procedure one more time. So since energy is mc squared, we have 939.38 MeVs is equal to the mass of the proton times c squared. So the mass of the proton is 939.38 MeVs per c squared, which is kind of close to 900 MeVs per c squared. Okay, part B. Antiprotons can be produced by accelerating and colliding two protons moving in opposite directions. A website suggests a possible outcome for a collision between these protons is described by the nuclear equation. So two protons colliding produce three protons and an antiproton. Deduced by using conservation laws whether it should be possible to produce an antiproton in this way. Okay, so in this equation, let's test the lepton number conservation. So lepton number is 0 before and it's 0 after, so it's conserved. I mean, there are no leptons involved anyway, so maybe using the lepton number here is, I don't know, an over kill maybe. So anyway, the baryon number now is 2 for the two protons, and for the three protons it's 3 times 1, and for the antiproton is -1. Okay, so it's 2, so it's good. Okay, so it works. The charge of the two protons is 2, and the charge of the three protons is 3, minus the charge of the antiproton, which has a negative charge. We get 2, so charge is conserved. But we have 2 times the mass of the proton going into 4 times the mass of the proton. So this violates conservation of mass energy. Okay, but it is still possible, if the initial kinetic energy of the two protons is 2 times 939.4 MeVs, which is equal to 1878.8 MeVs or higher. So you can still do it, but you have to provide this energy. So if I have two protons sitting, I don't know, here in my office, for example, actually this is my sister's office, okay? So if I have two protons sitting there, first of all, they will repel each other, so there is no chance they can interact, right? But even if they didn't, even if interacting was possible, you will still not get three protons and an antiproton. So you need to accelerate them. So that energy, the kinetic energy, is going to be converted into mass, which is the essence of special relativity by Einstein. Okay, this was question 13. Let's move on to question 14 now. Question 14 is another particle physics question. Okay, so the decay of a positive muon produced a positron, an electron neutrino, and a muon antineutrino. The diagram shows the tracks formed in a particle detector. So you can basically see that you have the muon moving in this direction, right? And then it decays into a positron and other stuff, okay? So let's actually read the questions that they ask. So question A muon belongs to a family of particles called leptons. State two features that all particles in the lepton family have in common. So first of all, they are fundamental particles, fundamental, meaning that you cannot divide them into smaller particles, okay? They have a lepton number of plus or minus 1. You can also write that they have a baryon number of 0, which again is an overkill. They have antiparticles. They interact via the weak force. That's another thing you can write. So interacting via the weak force, and have antiparticles, which are also leptons. And by the way, I don't know if I ever mentioned it in previous videos. So I'm a Greek speaker. I did mention that. So, but in Greek, leptos means thin. And they were named like that because initially they thought that they were light. You know, leptos is so lepton. It's a word used for very thin people. So, moving on to part B. Write a nuclear equation for the decay of the muon described above. Okay, so we have a positive muon, right? And we are told that it decays into a positron, an electron neutrino, and a muon antineutrino. Okay, so that's the nuclear equation, right? Okay, we have a positive muon, produce the positron, an electron neutrino, and a muon antineutrino. Okay, so that's the equation. Part C, describe the role of the magnetic field in a particle detector. So let's write the equation. First of all, so we can write moving, actually, charged particles. Let's write it that way. So charged particles moving in a magnetic field B, okay, bend, okay, because they experience force QVB. Now, that force is the centripetal force. So mv squared over r is QVB, right? So we can write that r is mv over qb, which is also equal to p, the momentum, over qb. So let's use a clean page. So this means that b bends particles. We already wrote that, I think, right? And because of that, the direction of curvature determines the charge of the particle, right? And we can see this from this equation. So R is P over QB. So if the charge is positive, it will bend, I don't know, this way maybe. And if it's negative, it will bend this way, okay? So it helps you determine the charge and the size of the curvature, right, tells you the momentum of the particle. Okay, so it achieves two goals at once, pretty much. Okay. Part D, explain how the diagram gives evidence that the particle or particles other than the positron were produced in this decay. First of all, if we go back, you see that the radius of curvature for the positron is larger than the radius of curvature of the muon. Okay. Oops, I didn't want that. I wanted something that looks more circular. Okay. It doesn't do it. Sorry. Anyway, but you get my point that the radius of curvature is different. Okay. So uh, the radius of curvature of the muon and positron are different. So what does this tell you? It tells you that the momenta is different. So since R is P over QB, then we know that P for the muon and the positron are different. So the momenta are different, okay? But momentum must be conserved, right? Hence, other particles, um, or just one particle are produced, balance momentum. Okay, question 15. A teacher demonstrates the electric field produced between two parallel metal plates. The plates are connected to a variable power supply as shown. Okay. The power supply has a very large internal resistance and includes a voltmeter that indicates its output. Uh, Question A, part 1. Add to the diagram to show the electric field between the two plates. Okay, so the positive side of the power supply is on the left. Okay, so that's the positive plate and that's the negative plate. Okay, between parallel plates, the electric field is uniform, right? And goes from the positive to the negative. Okay, so try to draw a few equally spaced lines like this. Okay, so the idea is that the space between the lines has to be the same. I mean, this gap has to be the same, right? So yeah, something like this is good enough. I mean, I put too many lines. Maybe we can put 3 or 4 or something like that. But yeah, I'm trying to teach it. So yeah, they have to be equally spaced because it's uniform and so on. Okay, part 2. Explain why the reading on the voltmeter indicates the EMF on the power supply. So we can write that because R is very large, okay, I is 0, so no current in the circuit, right? So with I equal to 0, there is no voltage, there is no voltage drop across the internal, across the internal resistance R. Therefore, the terminal voltage equals the EMF. Okay, and I remind you that the equation is voltage is equal to the EMF minus I times the internal resistance. So if I is 0, this is equal to the EMF. Okay. Okay, part B. The power supply output is increased until sparks are heard and are seen in the gap between the plates. Sparks form in the air when the electric field strength exceeds 3 times 10 to the 6 volts per meter and the air becomes conducting for a short time. Calculate the minimum potential difference across the plates for sparks to be created, and they give us the distance between the plates as 2 millimeters. So we can simply use E is V over D. Therefore, V is E times D, right? So 3 times 10 to the 6 times 2 times 10 to the negative 3 yields 6,000 volts. Quite high. Okay, explain why the voltmeter reading decreases significantly whenever sparks are produced. Okay, so during a spark, okay, current flows in the circuit. okay, because the internal resistance R is large, excuse me, okay, a large voltage drop um, occurs, right? Now, since the measured potential difference is equal to the EMF minus I times R, okay, then because I times R becomes large, V is less than the EMF and it's significantly dropped. Okay, and this is a complete answer, I believe. So, this was question 15, or yes, so we are ready to start with question 16. Okay, question 16. A student is investigating circuits that include a filament bulb. The filament bulb is labeled 1.5 volts, 0.5 watts. Show that the resistance of the filament bulb when operating normally is about 5 ohms. Okay, so first of all, we have to find the current that flows through this bulb, and we can do that since we know the power and the voltage. So power is current times the voltage, right? So current that we need is power over the voltage. So 0.5 over 1.5 yields 0.33 amps. So 0.33. Now, using Ohm's law, the resistance is voltage over current. So 1.5 over 0.33 yields 4.5 ohms, which is about 5 ohms. Okay. Part B is a long writing problem that awards 6 marks. And in my past paper videos, I always say that whenever you encounter writing problems, if they award 6 marks, you should provide about 6 marking points, meaning 6 sentences, in other words, or 6 statements that verify or nullify something that they ask you, or proves something that they ask you, and so on. So let's read it. The student wishes to control the brightness of the filament bulb using a potentiometer. The student connects the circuit shown. The total resistance of the potentiometer is very much larger than the resistance of the filament bulb. Explain how the brightness of the filament bulb changes as the potentiometer slider is moved from A to B. So when the slider is at A, okay, the bulb has zero potential difference, okay, so it's off. So that's the first sentence. As the slider moves from A to B, the potential difference across the bulb increases. Okay. So the bulb gets brighter and brighter as the slider moves towards B. Okay. When the slider reaches B, the potential difference across the bulb, is 1.5 volts. So the bulb is at maximum brightness at B, I mean. And another thing you can write is that as the slider moves towards B, okay, the resistance decreases. The resistance of, the combined resistance. So the resistance of the potentiometer plus bulb decreases because they are in parallel. Okay, decreases, and we can write in parentheses, they are in parallel. Okay, I think this is a good complete answer for part B. Let's move on to part C. The student connects the filament bulb in the circuit shown below. The capacitor is initially uncharged and has a capacitance of 1.2 farads. The resistance of the filament bulb is 5 ohms. Explain how the brightness of the filament bulb will vary as the switch is closed. By the way, I just thought about it. It wasn't planned in the script I have for this video, but I noticed that here they tell you that the resistance of the filament bulb is 5 ohms. Okay, this is what you need to answer in part A. Okay. So in part A, they tell you that show that the resistance is about 5 ohms. But anyway, I'm trying to say that sometimes you can read the second or third part of a question, and that will help you or guide you towards answering the first part in case you have trouble with the first part. Okay, I think this is useful with many problems. So anyway, let's read the question. Explain how the brightness of the filament bulb will vary as the switch is closed. Okay, so when the switch is closed, okay, the capacitor is uncharged. Okay, so the bulb gets the full supply and maximum brightness. Okay, now as the capacitor charges, it takes more of the power supply because voltage starts forming across its ends, right? So there is less voltage across the bulb, and current drops, right? So bulb dims. Okay, so the fading of the bulb's brightness is exponential. Excuse me, my handwriting is horrible today. Is exponential with time constant equal to r times c, which is equal to 6 seconds. Okay, so in other words, in about 3t or 18 seconds, the bulb will be off. Okay, but it will happen gradually. Okay, so you will see an exponential decay of the brightness from maximum to 0. Okay, so this is what's going to happen. All right, this was question 16. Moving on. Okay, question 17. Over 100 years ago, Rutherford supervised a series of experiments using a source of alpha particles and thin gold foil. Describe the model of the atom that Rutherford proposed as a result of this series of experiments. So they figured out that atom is mostly empty space, right? There is a charged nucleus, right? So all of the mass, or almost all of the mass is in the nucleus, which is positively charged, Okay, and the nucleus is small compared to the atom. Compared to the atom. Okay, and I'm saying this on the fly, but Rutherford's experiments, I think, um, took place in 1914, 1915, something like that. So, and then the neutron was discovered in 1932. So, in many questions, they sometimes throw the neutron thing into the mix. So, neutrons were not discovered by Rutherford. Okay, so they knew that there was a charged nucleus, but they couldn't figure out neutrons yet. Okay, so those were discovered later. Okay, part B. The initial kinetic energy of an alpha particle is 7.3 times 10 to the negative 13 joules. In a textbook, it is stated that an alpha particle with this energy will be brought to rest when it reached a distance of 5 times 10 to the negative 14 meters from the center of the gold nucleus. Deduce whether this statement is correct. So we need to figure out whether the kinetic energy given is equal to the electric potential energy when the alpha particle reaches very close to the gold nucleus. So how are we going to do that? So the potential energy PE is equal to 1 over 4 pi epsilon naught times the charge of the gold nucleus times the charge of the alpha particle. Oops. Okay. So the gold nucleus has 79 protons and the alpha particle has 2 protons. So we have to multiply their charges. And if we divide by the distance, this is the electric potential energy. So the electric potential energy, actually, let's denote it by U. Okay, so U is equal to charge times the electric potential, pretty much. Okay, and in this case, the charge is 2e, and the electric potential is that of a gold nucleus. So that's 1 over 4 pi epsilon naught times 79e over d, where d is the distance from the gold nucleus we are interested in. Okay, so let's multiply, let's plug in numbers. So we have 8.99 times 10 to the 9, because we can actually cast this into k, and k is 8.99 times 10 to the 9. And the units are newtons per coulomb squared per meter squared, right? Times meter squared, excuse me. Okay, so let's, if we multiply, excuse me, 79 times 2 is 158, and then we have 1.6 times 10 to the negative 19, which is the charge of one electron, and then we have to square it because we are multiplying, and then over 5 times 10 to the negative 14 meters, which is given to us, and this yields 7.27 times 10 to the negative 13 joules, which is about 7.3 times 10 to the negative 13 joules, which is equal to the kinetic energy. So yes. Okay, so this works, I mean. Okay. Part 2, determine the initial momentum of the alpha particle. So the kinetic energy is p squared over 2 times the mass of the alpha particle. So the momentum is equal to the square root of 2 times the mass times the kinetic energy. So we have the square root of 2. Now, what is the mass of the alpha particle? So it is not given to us. So whenever they don't give you the mass of an element, so let's say you have the element X with mass number A and proton number Z. So its mass, if it is not given to you, can be, you can use A, the mass number, times U atomic mass units. Okay, so the mass number is 4. So 4U. pretty much, okay? And I'm going to substitute this U actually. So the mass of one atomic mass unit is 1.66 times 10 to the negative 27 kilograms, which you can recognize as very similar to the mass of one proton, pretty much, okay? So I hope things make sense. And then times 7.3 times 10 to the negative 13. And the answer is, I'm going to write it down there. So I'm going to write it here. So the answer is 9.84 times 10 to the negative 20 kilograms times meters times seconds to the minus 1. Okay, part C. An alpha particle moves along a path directly towards a gold nucleus as shown. An elastic interaction occurs and the alpha particle recoils. State what is meant by an elastic interaction. So it means that the kinetic energy is conserved. This is what elastic means. Okay. And part 2, state what happens to the atoms in the gold foil as a result of this interaction. So the gold nuclei recoil. But most of the momentum is carried by the alpha particle, okay? Because the gold nucleus is massive, so it doesn't move too much, okay? And this was question 17. Okay, question 18 is the last question in this paper. And it's something that I think I've heard before. When I took the train, I used to live in the United States, and I used to take the train. At some point, I lived in Western Illinois, and there was a train that took you to Chicago in 4 hours called Amtrak. You can search it up. So I think that train had this mechanism to stop, okay? Because back then I was teaching electromagnetism in a small college in Illinois, and we talked about this, I think, but that was long ago, so I don't remember the details. So um, let's do this. The last problem. Regenerative braking supplies a current back to the power transmission system whilst slowing a vehicle. The arrangement shown can be used as a regenerative braking system on a train. Excuse me. Okay, and we see the arrangement here. So this coil rotates in this magnetic field pretty much. Okay, so you have this kind of rotation. The coil rotates with the wheels of the train. Two copper rings are connected, here they are, to the ends of the coil. The rings rotate with the coil, and two carbon blocks make electrical contact with the rings as they rotate. Describe how this arrangement can be used as a regenerative brake. So let's start by stating that a rotating coil, right, gives um, gives a changing magnetic flux linkage, right? Because it cuts through the line of this magnet. So this induces an EMF and current. And why do we have current? Because we have a closed loop. Okay. The induced current, okay, opposes the charge sorry, not the charge, what did I say? So let's go again. The induced current opposes the change that created it. Okay, so the wheels slow down uh, and the system acts as a brake. And I'm assuming there must be a mechanism over here that it is turned on and off. So because if this is on all the time, the train will not move at all, right? So they probably establish a connection the moment they want the train to stop, I assume. So if you know how it actually works, or if you've seen something like this, let me know in the comments. So let's move on to part B, to question B. So, a specification for a new train states that the train should be able to accelerate to a speed of 360 kilometers per hour from rest, and that this acceleration should be completed within 40 kilometers of level track. The graph shows the performance of the train on a test run. Okay. By the way, speaking about Chicago, the trains in the United States are capped, I believe, to about 120, maybe 140 kilometers per hour. I think for safety reasons and stuff like that. So you don't have really fast trains in America, and there are not too many trains, especially passenger trains. And I don't want to get into politics. I don't like talking about politics, especially in a physics channel. But there are reasons for that. I think the problem is that to establish fast trains like those I don't remember, there is a very characteristic name for them, but there are magnetic levitation, I think maglev trains in France and in Japan that move really really fast. But to make those kind of trains available in the US, you will have to re-establish new tracks, which costs too much. I mean, America is a huge country, so I think for reasons like this, fast trains do not really exist. So anyway, but yeah, I mean, it's this is outside of my depth. So yeah, let's move on with the physics. So question I. Calculate the acceleration of the train as it accelerates to a speed of 360 kilometers per hour. So you can see that pretty much the acceleration is constant up to, okay, 360 is, so this is 350 over here, this point. So this is let me think. So we have 360 is the next box over here. So this one. So 360 is that point over there. So you see that the acceleration is constant. The line is straight. So we can use the fact that the gradient is delta V over delta T. And it's pretty much the acceleration, right? And we can use that point over there, which is 360 times 1000, because it's in kilometers, right? And then this takes place at 450. You can see it here. So within 450 seconds, it accelerates to that speed. But then because 360 is kilometers per hour, we have to multiply by 60 times 60 to convert to seconds. So the answer is 0.22 meters per second squared. Okay, and in case I confused you, 360 kilometers per hour is the same as 360 times 1000 meters, and then 1 hour is 60 minutes, and 1 minute has 60 seconds. So this is the equivalent, and you can do the calculation on your own. So pretty much this is let me think, 3,600. So over 36, so that's what, 100, right? Is that correct? So 360, I'm using my calculator. Yeah, that's correct. Okay, and this is now in meters per second. Okay, moving on to part 2. Deduce whether the performance of the train met the specifications on this test run. So let's use that. So let's use v squared is u squared plus 2as with the initial speed equal to 0. So v is uh, we've we found it earlier actually. So v is 100 meters per second, which corresponds to 360 kilometers per hour. So we're looking for the distance. So s is v squared over 2a. So we have 10,000, which is v squared, over 2 times 0.22, which yields 22,500 meters, which is 22.5 kilometers. So yes, it accelerates to the desired speed in 23 kilometers, more or less. And the specification says that it should accelerate to that speed within 40 kilometers from the start. So that's good. So it works. Okay. Part C. On curved tracks, there is a maximum safe speed for the train. Explain why there is a maximum safe speed for a train traveling on a curved track. So a train moving, around a bend, experiences a centripetal force towards the center. Towards the center, okay. And whenever we say center, we mean inwards, pretty much an inwards force. This is provided. This force is provided by the wheel, by the wheel rail contact. Sorry. So this force is provided by the wheel / rail contact force. Okay, and let's move to a clean page to complete this problem. Since F is mv squared over r, the faster the train moves, okay, the more centripetal force is it needs, to stay on track. Okay, there is a limit to how much force the track can provide. So there is a limit. So it might break actually. The rails. There is a limit to the force the rails can provide, right? So above a certain speed, the train cannot stay on track. Okay, so I hope this makes sense. So yeah, if the train goes around a bend, pretty much, it has to lower its speed to make sure it stays on track. Okay, so that's the main point, the main takeaway point from this question. Okay, and now part 2 of question C. When the train travels at 200 kilometers per hour, The minimum safe radius of curvature of the track is 1800 meters. Calculate the minimum safe radius of curvature for a speed of 360 kilometers per hour. And because we don't have enough space, we're going to move back to the clean page. So this is part 2 now. So let's call it F safe is equal to mv squared over r. So v squared over r is F safe over the mass, because they don't give us the mass of the train. So F safe over mass is equal to 200 squared over 1.8 kilometers. So I'm using weird units for this quantity now, and 200 is in kilometers per hour. So we have kilometers squared over hours squared. Okay. Oops, we don't cancel the hours. Excuse me. So this is equal to 22,222.2 kilometers per hour squared. So this is the safe force per mass. If the velocity is now 360, so for 360 kilometers, we need 360 squared, and this is kilometers squared over r, and we need this to be equal to the safe force per mass, which is 22,222.2 kilometers per hour squared. Okay. And by the way, I forgot to divide with hour squared. Okay. So first of all, let me separate this. So so this part is the numbers. Okay. Okay. So let me delete this and that. So kilometers per hour. So this is r. Okay. So hours cancel and kilometers cancel. Okay. So r in this case will be, if you do the calculation, you will find 5.83 kilometers. Okay. I hope this makes sense. And the reason why we did this weird division by the mass is because we are not given the mass. So we had to work around that. All right. So this is about equal to 6 kilometers. All right. So this was paper 1, Advanced Physics 1, from the 2024 examination season. Okay. Let me know if you find these videos useful, if you want more. I mean, of course you want more, but okay, I mean, there are only 24 hours in a day, so I do my best, guys. Thank you for those of you who comment on the videos. Please like, subscribe, leave a comment, and help me grow this channel. Okay, so thank you, guys, and see you in the next video. Bye.